So this is the last video for the 422 class, and I'm recording audio after the fact. And we're going to go through usually 4 steps to solve Laplace transform circuits. First one is to find initial conditions. We did that in 285. This requires no differential equations, requires no Laplace transforms. It's to just find the voltage across the capacitor and the current through the inductor. Here in this circuit, we're going to solve the simplest RC circuit, but in Laplace transform world. And the initial condition is given. So step 1 is done for us. It's 3 volts on the capacitor. Now the second is to draw the circuit in S domain. We're going to draw it using the initial condition, using the previous video that I just recorded. And then we're going to use the traditional electrical engineering, methods to solve the circuit, which are nodal mesh, Kirchhoff's law, Thevenin superposition. And then we're going to find the inverse transform and hopefully get, for example, the current as a function of time. So the question here is to find I of t. There is 5 volts starting at t equals 0. Actually, it's I of t for t larger than 0. There's 5 volts on the left side. The capacitor has 3 volts. So there's really in the beginning 2 volts there. And that current starts off as a 2 volt difference on the resistor means 2 divided by 1K. We're expecting it to be 2 milliamps. The capacitor is going to charge to 5, and then the current is going to go to 0. So hopefully everybody has an intuitive notion of what an RC actually does here, that the forcing function is 5 volts. The capacitor is already charged at 3, maybe by another voltage supply that was turned off. And now we want to get to that end, which is the 2 milliamps beginning current going to 0 really fast, I guess. Let me see. RC is the constant, and it's 10 to the minus 3. So it's 1K times 1 microfarad, 1 kilo ohm times 1 microfarad is 10 to the minus 3. So 1 over 10 to the minus 3 is 10 to the third. So I'm going to redraw, or I have just here redrawn the circuit in S domain, and I'm adding a power supply for the capacitor. So this will have the 3 volts, which is the initial condition, and this is going to be 3 over S. And now we can solve the circuit just like we did in 285, or we did in the beginning of this class. Actually, this whole last year we've been solving it like this. But now the current we're going to get is I of S, so it's in the S domain. So obviously I can merge those 2 power supplies. So there's the 5 and the 3. We also have been doing this for a long time. Hopefully everybody understands how I got 2 over S here. And then there's 1 kilo ohm, and then the capacitor. The question is still, what is the current? And the current is going to be the voltage divided by the impedance. And the impedance is the sum of the 1K with the 10 to the 6 over S. And I'm going to take a shortcut here. Instead of doing the cutting the S's and multiplying S by 1K, and then these 2 S's cut, I'm going to just divide the 2 by the 1K to actually have S with a coefficient of 1. So really the final formula for I of S will be 0.002 divided by S plus 1,000. I hope this is correct, and if I made a mistake, please post in comments here. But this is a normal formula for equation for a low-pass filter. And we also know the inverse transform. So now it's straightforward to get I of t. And those 0.002 is the 2 milliamps. And I'm going to write 2 milli, but I could have written just 2 and then instead milliamps instead of amps as a dimension. And then it's the e to the minus 10 to the 3t, 1000t. And that means the tau is 10 to the minus 3. Right, but I'm putting the tau on the numerator here. So that's the time constant. This is exactly what we did in 285. I promise you'll have some very similar circuit in 285 or in chapter, let me see, chapter 7 of the Alexander and Sadiko book. If you want to go back and use now those circuits to try to solve again, but using Laplace, it should show up as much simpler.